Let's continue with our chapter 9 by talking about Pascal's formula and the binomial theorem. So this is really going to build on something I've already hinted at in some of the past videos from chapter 9. So the first thing is, I don't know if you're familiar with Pascal's triangle, but it's actually very, very important and it's a crucial component. It's the idea that gives us the form of key identity for um, combinations, or what are known as the binomial coefficients. The biggest thing about it is the Pascal's formula, which is based on his triangle. And you may have seen his triangle looks like this. I'm gonna write down because this will come back. Well, sometimes it's written in centered, so it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so forth. And many people can see that everything is a combination of the two things that are directly above it. If you simply add the values directly above it, then you get those values. Well, obviously 0 plus 1 is 1 and so forth. And so kind of seeing that trend actually gives us root to this key formula from Pascal, namely that the sum of any value, choose R, is the previous is 1 less of that value, choose R minus 1 plus and choose R. Now, that's not really, this is where sometimes people talk about this. There's a lot of other things that are actually proven and really beautiful proofs of this, but it gives you the idea about how this, where this comes from. Looking at the table is not really a proof, but it kind of gives you the idea of why it works and how it's based. And actually, that's part of the reason that Pascal came up with that table, was he noticed this arrangement. Now, by the way, these happen a lot. And they're highly powerful because this is really beautiful. Now, this formula makes it really easy to do our combinations, especially when we start getting bigger and bigger and bigger, because we can simply, if I know how to do something, I can then make a recursive function based on the previous values. So if I want to find something, and that's what it's just trying to show here, this is a Pascal's triangle set off to the side. So it's oriented, instead of being down the middle and side to side, it starts here and comes down. Now, the problem here is this actually should have a second one right here. There's one missing in this table that they have. Now, sometimes, quick note, even though this is attributed to Pascal, was actually discovered, just like some of you may be familiar with Euclid's elements or a number of other key formulas. You might know the, I just lost the word. Pythagorean theorem. Many of these were actually discovered centuries before by the Chinese, by those in uh, the Arabs and so forth in that portion of the country, in Egypt and India. There's a lot of different cultures that have actually discovered many of these things separately. Now, we call it Pascal. Honestly, it's a Western culture trend because his paper was published versus the other ones were written and not published as aggressively. They're simply known and written down within a culture and so forth. And that's the reason that it comes down to commonly being known that. But again, that doesn't. And Pascal, by the way, didn't steal it from someone. He discovered it independently, but it had already been discovered previously, and therefore that's why it is. So Pascal's triangle, let's just look at it real quickly. If I want to compute the values of 6, choose 3, and 6, choose 2, well, this right here is going to be equal to 5, choose 2, plus 5, choose 1, because I'm going to make this number 1 less and this number 1 less. Well, 5, choose 1, that's always easy. Any number, choose 1. K, choose 1 is always K. Because I have K things. How many ways are there to choose 1? Well, there's K ways to do it. That one's pretty easy. As for the other values in here, 5, choose 2. Well, that one, I'm going to write it out real quickly. That's going to be 5 factorial over 2 factorial times 3 factorial, or in other words, 5 factorial, not 5 factorial. I don't want 5 factorials. I could write that also as 5 times 4, because that's where the 5 factorial divided by 3 factorial will get rid of everything else, over 2 times 1, and these things cancel out to equal just a 2, so that's going to be 10. So I have 10 plus 5, which is 15. And now we can do another way to check that out. If I really want to do the same thing like I did here, turns out that this is equal to 6 factorial over 2 factorial times 4 factorial, which again is 6 times 5 over 2, which is 15. Bigger. And the same thing here. I would break this one up into two values. Now you would break this up into 5 choose 3 plus 5 choose 2. Now we already know 5 choose 2, and it's 10. Now the really nice part is 5 choose 3 is equal to 5 choose 2, because there's a different identity, which is 5. I shouldn't say 5, I should say n. N choose k, and I've already mentioned this one before, is equal to n choose n minus k. Because this is choosing the k things that I want. This is choosing what I don't want. But if I choose what I don't want, then all that's left over is what I want. So it's counting the exact same thing by just counting the opposite. So this is the really cool way. It's highly valuable and really useful for us to use this. All right. And again, that formula is this right here. Now, again, that's really valuable because of what is known as the binomial theorem. So the binomial theorem is this, and it's kind of useful and something maybe I'm going to go back and show you something. If I have two numbers, a plus b raised to a power, then that is actually going to have the coefficients are going to be n choose 1 and choose 2 and so forth all the way up to the end. This first number, even here in front of the a, is actually n choose 0. And in front of the b is also n choose n, both of which happen to be 1. But let me just go back to here, and I want to show you something real quickly to kind of build on this. So let's go back to, I'm going to write the Pascal's triangle over here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And hopefully all of you learned this somewhere in your algebra. This is where this triangle can be super valuable. Well, if let's say I have x plus y and I raise it to the first power. We notice that's 1x plus 1y. So when I raise it to the first power, I got this line. If I take x plus y and I square it, from your days previously, you could have multiplied this out, but anyways, you get x squared plus 2xy plus y squared. Notice coefficients, so I add the ones in here, match perfectly. And you can actually use it then to say, what is x plus y cubed? Well, it's going to be 1 times x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Now, the reason for that is this. Let's look at this for a second. This really is going to x plus y times x plus y times x plus y. So my first option, if I want nothing but x's, so I'm going to get an x cubed. The question is, how many ways are there to do that? Well, I have to pick this x, I have to pick this x, and I have to pick this x. So I have to pick I have 3 things, and I have to pick all 3 of them. So that's what's going to give me 3, choose 3. I have to pick all 3 of them. The next number is, notice I have 2 x's and a y. So I pretty much am saying I have 3 things, and I have to choose 2 of them. Or you could have said here, I could have said 3 choose 0 because I said how many y's am I choosing? Choosing 0 y's. Here I could 3 choose 1, but prefer to call it that way. And again, this is the beautiful symmetry of these numbers. If I 3 choose 1, how many ways are there to choose y? Well, I pick one y out of 3 things. And then the next number, this one, would then be the 3 choose 2. So the reason is we're looking at this, we're saying I have 3 different x's. How many ways can I pick them? Or I have 3 y's. How many y's am I picking? How many ways are there to do that? And so that gives us actually, ironically, the coefficient. That's actually why we call this symbol the binomial coefficient. It's because it is literally the value that leads off on it. So, and that's where we can do this, where I'm starting off the first term is n choose 0, and then the last term is n choose. And the other thing is a couple of numbers to remember is that for any non-negative integer, that to the 0 power is 1. And previously it's n times n times n minus 1 because we're simply breaking it up into the different parts. And so this starts making a little more sense about where these numbers are actually coming from. So these are actually the same exact things. We're just actually applying them over and over and over again and getting our answer of what it fully looks like. All right, let's come here and let's kind of talk about how this is beautiful and really nice. So I want you to pause the video and I want you to find a plus b to the 5th power using this. Go ahead and pause the video and do that. All right, so if you did that, you should get this, which is really, I'm just doing this as a summation. 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and then the first and last term. And notice this can be a to the 5 minus 1, a to the 5 minus 2, and then b is to the 2 power, and so forth and so on. So the minus, whatever this is minus, this has to be, because the total sum of their powers has to equal 5. Because we're choosing 5 things, just some of them are going to be a's and some of them are going to be b's. And if you do 5 choose 1, well, that's 5. 5 choose 2 is 10. 5 choose 3 is 10. We've already done this. And 5 choose 4 happens to be 5. Okay, let's go back. This one, x minus y minus 4. What's that going to be? Well, it's going to be the same thing, but here's the catch 22. My second term is not just a single value, but it's actually the minus 4 times y. So this first term here is negative 4y, negative 4y squared, negative 4y cubed. So this ends up throwing it off because when I take care of this, raised to the first power is still negative 4y. But when I take this to the second power, it's positive 16y squared, negative 64y cubed. Because remember, this power is going to impact the negative, the 4, and the y. And then I can distribute. So while this does not look, if you look at this, you're like, that doesn't look like Fibonacci sequence. All of these values before do look like a Fibonacci sequence. It's the fact that I had this 4 right here that's actually making it not quite live up to what it needs to be. All right. So let's actually then find the value of this in terms of closed form. Well, if you look at it, I could start writing this out and be like, this is going to be really, really annoying. I don't want to write this out as a bunch of sums. So if I was writing it out as sums, as a reminder, this is going to be, first term would be n choose 0 times 9 to the 0 plus n choose 1 times 9 to the 1 plus n choose n minus 1 times 9 to the n minus 1 plus n choose n 9 to the n. Like, oh, great, I got to add this whole thing up. But there's actually something super subtle that's actually staring us in the face for the problem, and we're not even seeing it. It's this right here is really times 1 times n minus k. Because 1 to any power is just 1, and multiplying by 1 doesn't change anything. But if I write it like this, The sum of these two things is n, and that distinctly tells me that I'm actually going to have this 1 plus 9 to the nth power, because what we have here is actually the binomial theorem. Remember, this was what the binomial theorem was. So I get 1 plus 9 to the nth power, which is 10 to the nth power. All right, I hope that gives you a taste. These are really valuable tools, and actually we use them a lot more as we go deeper into combinatorics and graph theory and further in discrete math. Are we going to use them a lot in this class? No. The bigger thing is I want you to recognize it because it allows you to break things up into much simpler problems by this kind of manipulation like this. And that's just a very, very common thing we do because believe it or not, we do solve a lot of things very symbolically that actually computers cannot yet do, even with AI. Good luck, and let me know what questions you have.